I'm Prapurna. I did my master's in structural engineering from NIT Jamshedpur. Today, I'm going to present the topic on theories of failure. First of all, what is theories of failure? Basically, if you see this graph, you have the stress strain curve for both ductile and brittle materials. What in all the strength of material test we do, we basically do the test in uniaxial loading. Means the stress strain graph obtained here is for uniaxial loading. So in practical life we have different stress components acting, not only the uniaxial loading, we have biaxial loading, triaxial loading. So you have to deduce the results of the uniaxial loading and apply them to the three-dimensional or biaxial loading, whatever it may come. So for that we need certain theories of failure, how we can predict the failure of a material in real life. If we know the theories of failure, we can give some safety factor and design the components of the structure accordingly. Okay. Coming to this slide, we are telling about theories of failure. Where do we use? Means here the explanation of what I told in the previous slide. Here, when a body is subject to uniaxial loads, prediction of failure is very simple. So any of the failure theories can be used if we know the quantity of interest. Let it be shear stress, let it be principal stress, principal strain. Anything can be predicted easily. However, in case of biaxial and triaxial loading, we need to predict so that the structure will be safe. In case of mechanical, we wanted the machine to be safe. Okay, check whether it is less than the allowable value or not. So if it is exceeding the allowable value, we can say that material is failing according to this theory. So the allowable values are derived from stress strain values obtained in the uniaxial test. Okay. So while designing any member subjected to any state of stress, we compute the principal stresses, enhance the quantities of interest to predict if it is safe using various theories of failure. So ultimately what we are using? So basically we use the results of the uniaxial tension test to predict failure under multi-axial loading. So in the absence of these failure theories, we have only to do experimental testing, which will incur lot of cost to us. So to avoid that, we have made certain theories to predict the failures. And what are the theories of failure? So based on the loading condition, tensile load, compressive load, shear load, material behavior like ductile, plastic, brittle, there are five main theories of failure. Okay, maximum principal stress theory, it is also called Rankine theory. Maximum principal strain theory, also called as Saint Venant's theory. Maximum shear stress theory or Tresca gas theory, maximum strain energy theory or Haig's theory, and maximum shear stress theory or von Mises and Henckey theory. Okay, why we are proposing these many theories of failure? Basically, they predict, every researcher did took some quantity of interest like principal stress, principal strain, and formulated certain theories. Out of this we will find which theory fits the material. But what if the material is of different nature? Some material is of ductile, some is of brittle nature. So which theory will suit which material? That one we need to figure it out. one more important point when discussing the theories of failure is, will brittle material and ductile material will exhibit the same nature under the loadings? No. In case of brittle, let me explain the pen. In case of brittle, it may experience the triaxial loading, it may fail under it, but ductile need not fail under the triaxial loading. When you take a material it is subjected to triaxial loading, if it is of brittle nature, it might not it may fail in triaxial loading in under hydrostatic stress, but the ductile material need not fail by hydrostatic stress in the triaxial loading. It may fail by deviatoric stress. So what is hydrostatic and deviatoric stress? If you take a material, suppose this specimen, if it reduces its volume, if it cause the reduction in volume under the triaxial loading, it is the hydrostatic stress that is responsible for its reduction in volume or the distortion. So what is deviatoric stress? So deviatoric stress is when the material is subjected to triaxial loading, it may experience certain portion of shear. It will experience shear, so it will fail under shear. So ductile materials mostly fail under shear rather than the hydrostatic stress. So in our theories of failure, we will account for hydrostatic stress. So which theory fits into which domain? Our first theory is maximum principal stress or Rankine's theory. This theory here, in this case, a complex loading, when the maximum principal stress reaches the ultimate stress or yield stress of the material, the component will get failed. Here the component of interest is principal stress. We will consider the maximum principal stress of the specimen chosen, and we will compare it with the yield stress that we obtained from uniaxial tension test. Okay, as brittle material is weak in tension, this is mostly suitable for brittle materials. So the most suitable theory for brittle materials is maximum principal stress theory or Rankine theory. That how we are comparing is, in simple tension, sigma 1 equals to sigma yt, means sigma yt is the ultimate tensile stress when you are subjecting the specimen to uniaxial tension test. Okay, if it is in compression, it is the ultimate compressive stress, and you are taking sigma 2 is principal stress. So when you are meeting this condition, this particular condition, you can say the material is failing. So if you need to include factor of safety during design, so we will consider sigma 1 yt by factor of safety. That means we are allowing the material only up to a certain point, rather than if you are taking this as permissible, we are limiting the permissible stress with this factor of safety. Next theory is maximum principal strain theory or Saint Venant's theory. According to this theory, the components are safe if the maximum principal strain at a critical point in the loaded member will not exceed the strain under the yielding condition when subjected to uniaxial loading. It is clear here we are considering our component of interest as principal strain. So how do you get strain? Sigma 1 equals like when you are comparing strain you know when it is subjected to triaxial loading, sigma 1 minus mu into sigma 1 sigma 2 plus sigma 3. This is the maximum principal strain where mu is the Poisson's ratio. It should be less than the uniaxial tension test stress from the uniaxial tension stress divided by the elasticity modulus or Young's modulus of elasticity. Okay, so this maximum principal strain theory is most suitable for all the materials like ductile, brittle and material under hydrostatic conditions. That means which will cause the material to distort. It's its reduction in the volume. Okay, and this is the failure criterion plotted for a 2D stress condition. How do you get 2D condition? Here when you are taking sigma 3 as 0, we are uh, modifying the equation as sigma 1 minus mu sigma 2 should be less than or equals to sigma yt by E. In this way you are going to plot this. And maximum shear stress theory or Tresca gas theory. Maximum shear stress theory is one of the failure theories used for the safe design of mechanical components, and it is suitable for the ductile material. The maximum shear stress theory is also called Tresca theory of failure. This is not suitable for hydrostatic stress condition. We already discussed a ductile material mostly don't fail by hydrostatic stress condition. It will experience a certain portion of deviatoric stress. It will fail under that. For that you can't apply every possible theory of brittle that will satisfy brittle materials also to ductile materials. For this particular purpose, we are taking shear stress as our component of interest, and we are validating with the applicability to the ductile material. The maximum shear stress theory says that failure will occur when the maximum shear stress exceeds the shear stress at uniaxial loading. So, the maximum shear stress that we will obtain from either biaxial or the triaxial loading that we are choosing, it should be less than the uniaxial loading shear stress. Okay, and that can be numerically represented as tau max is the modulus of out of this, what is the maximum? Sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 3 by 2, sigma 1 minus sigma 3 by 2. This is the maximum shear stress in triaxial loading. We know when you plot the Morse circle, we will get the shear stress is the radius of the Morse circle, where the if it is sigma 1 sigma 2, you will take sigma 1 minus sigma 2 by 2 as the radius of the Morse circle, that is the shear stress. But when there is a involvement of triaxial loading, we have to take all the components. So tau max is the maximum of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2 and sigma 1 minus sigma 3 by 2. And we know tau max is equals to like we should validate that with sigma y, where it is the yield stress in the obtained from the uniaxial tension test, sigma y by 2. So the condition of failure is sigma 1 minus sigma 2 by 2, it should be less than or equals to sigma y by 2. And all these are the conditions of failure in the three-dimensional loading, like triaxial loading. Okay, so it is simplified as like this. So when you plot it for 3D where sigma 3 is 0, you can represent it in the 2D form, like this is the failure plane when you consider in a plot. The next theory is maximum strain energy theory or Haigh's theory. As per the maximum strain energy theory, failure occurs when the total strain energy in the fundamental component exceeds strain energy under yield condition. According to this theory, strain can be fully recoverable up to the elastic limit. However, this theory will not give results in case of triaxial loading having almost equal magnitude. So, the strain energy theory is developed. Strain energy is developed and stored in the material after the elastic deformation. This energy will also be the work done during the elastic transformation. This theory says developed strain energy will be responsible for the strain energy under yield condition. Failure for strain energy under yield condition. The what is the component of interest in this theory is strain energy. How you get the strain energy for three-dimensional stress system? Like this. See, u equals to 1 by 2e into sigma 1 square, sigma 2 square, sigma 3 square minus 2 mu into sigma 1, sigma 2, sigma 2, sigma 3, sigma 3, sigma 1. This is the strain energy per unit volume when it is subjected to, when the material or component is subjected to three-dimensional stress system. Okay. So, what is the value of strain energy per unit volume corresponding to the yield point of a material under tension test? So, under uniaxial tension also we need to get no to for comparison. That's the yield point. So, that is 1 by 2e into sigma t square, where sigma t is the principal stress at elastic limit under tension test. Okay. So, for two-dimensional stress system, we already know that sigma 3 will be 0 for two-dimensional. So, the condition of failure will be reduced to this. How you got that? We are equating sigma 3 as 0 here and you are substituting. So, it is like this. So, when the material is failing, what it means, it is the strain energy, maximum strain energy of that specimen is exceeding its principal strain energy, maximum principal strain energy obtained from the uniaxial loading test or tension test at elastic limit. Okay. So, what is the condition for safe design? So, when you wanted to design it under safety, so what should be taken? Factor of safety needs to be considered. So, then the maximum to avoid that to avoid this failure, we are limiting the maximum value of strain energy per unit volume under the permissible strain energy. What is the permissible strain energy? Principal stress at elastic limit divided by factor of safety. That is permissible principal stress. When you apply that, what is the condition we will get for the safe design when you are designing according to strain energy theory? Sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu into sigma 1 plus sigma 2 plus sigma 2 plus sigma 3 plus sigma 3 sigma 1. This equation should be less than or equals to sigma t by factor of safety whole square. For two-dimensional system, sigma 3 is 0. When you substitute that, you will get this. Okay. And this is the failure plane when you plot it in 2D system. This graph. So, what is the maximum shear strain energy theory or the von Mises-Henckey theory? It's also known as maximum distortion energy theory. It is introduced by the scientists von Mises and Henckey. So, it is also called von Mises-Henckey's theory. Here, when the loads are applied to the component, it will deform, due to which the size and shape of the component will also change. The energy responsible for changes in shape and volume is known as distortion energy. Maximum shear strain theory state that distortion energy associated with the unit volume of the member exceeds the distortion energy at uniaxial loading per unit volume at failure. Okay, at failure, maximum shear strain energy exceeds the shear strain energy or distortion energy at uniaxial loading. So how you are comparing it mathematically? So let us consider a three-dimensional system where sigma 1, sigma 2, sigma 3 are the principal stresses uh, of the material developed in the material under tension test. Okay, the shear strain energy per unit volume is u equals to 1 by 12 e into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So at elastic limit under tension test, sigma t will be the sigma t is the principal stress developed in the material. As it is uniaxial loading test, other components will be 0, sigma 2 and sigma 3. So the shear strain energy per unit volume corresponding to the yield point of the material under tension test. At the yield point, what will be the shear strain energy? It is ut equals to 1 by 12 e into 2 into sigma t square. So what is the condition of failure? The total strain energy per unit volume means this equation. If it exceeds this particular equation, when the yield point shear strain energy per unit volume at the yield point under tension test, the material is failing. So what is the condition for the safe design? You need to take the factor of safety. That means you need to limit the shear strain energy. It should be less than the permissible value. That means the permissible principal stress is equals to principal stress at elastic limit divided by the factor of safety. So for three-dimensional stress system, what will be the equation? Sigma 1 minus sigma 2 plus sigma 2 minus sigma 3 plus sigma 2 minus sigma 3 whole square should be less than or equals to 2 into sigma t whole square. Okay. For 2D system, sigma 3 will be 0. Factor of safety whole square. Here also sigma t by factor of safety whole square. So this is the for 2D condition. If you plot the failure criterion, failure plane, it will look like this. If when your component of interest is maximum shear strain energy and the 2D two-dimensional stress system. So what is the conclusion from this lecture is, when you are dealing with brittle materials, uh, we are considering maximum principal stress theory or Rankine theory suits best for it. And when you are dealing with ductile materials, maximum shear stress theory or Tresca gas theory will suit it the most. Thank you.